you for inviting me to give this talk. And I hear who you are. And my understanding is that the background knowledge varies a little bit. So part of my talk may be too difficult for some of you. Sorry, you can ask questions. Some part of my talk may be too easy for you. Sorry, please just be patient. And I'll start. Are you now? Oops. Can you see? Are you now? Do you see my slide now?
Yes, we can see the slide.
Introduction. Yeah. So my name is Takashi Sekii. I belong to NAOJ, National Astronomical Observatory of Japan, and Sokendai. Okay, now let's start with this guy, Arthur Eddington. Now, I realize that he may not be very popular in your country because of what he did to Chandrasekhar, but you have to admit he was one of the greatest astronomer of his time. And here is a quote from his book. Let me read it. At first sight, it did seem that the deep interior of the sun and stars is less accessible to scientific investigation than any other region of the universe. Our telescopes may probe further and further into the depths of space, but how can we ever obtain certain knowledge of that which is hidden behind substantial barriers? This is in the foreword of The Internal Constitution of the Stars by Eddington. Okay, so here's a question asked. And Eddington's answer is stellar evolution theory, and hence this book. And now we know there another answer, and that is Helio and Asteroseismology. So this talk is going to be about introduction to helioseismology, how does it work, and what have we learned. And then introduction to asteroseismology, and what are the differences between Helio and asteroseismology. And let me pick just a single example of asteroseismology of KIC 111-45123. And because of the request by Veldant, I talk briefly about the admission process at our graduate university. And now first, about the sun. About the sun, we know these quantities. These are either almost directly observed or indirectly observed, but these are observed quantities: mass, radius, luminosity, and even its age. We also know a few things from the modeling. This is the Eddington's way, okay? So we build the standard solar models. Actually, there are more than one. Yeah, some people think there's only one model, which is the standard model, but that's not true. There are more than one. We know, for example, the center temperature is 1.5 times 10 to the 7th Kelvin. And we know that the energy is generated at the core by hydrogen fusion, and these energy are eventually emitted to the space. And also because of this hydrogen fusion reaction, the chemical composition changes. And this brings about a process called evolution. Now, how do we build a solar model? Now, we start by decide what are the initial mass and the chemical composition. How much of what? Like 3 tons of water. So this we have to decide. Okay, the sun became a star 4.6 billion years ago when hydrogen burning began. It is known from physical argument that at this time the sun was fully convective, and because it was fully convective, it was the chemical composition was uniform. In this case, we can easily calculate the structure of the sun. And what about afterward? The time evolution then on can also be calculated, assuming a spherical symmetry and the hydrostatic equilibrium, namely the gravity and the pressure gradient are balanced to keep its shape. Then we also know the nuclear reaction rate from the, okay, someone chat, sorry. Okay. nuclear reaction rate from physics. Well, actually, we don't know them so well in some cases, but let's say we know them. We know, and then we can calculate a new chemical composition profile in the next time step, so to speak, and then we can calculate the structure of the sun in the next time step, and then we can continue this. So the basic info we have got. One is the mass. Okay, this solar mass we know from the gravitational force. The length of the year on Earth is determined by solar mass. If it is bigger, 1 year will be shorter. If it was lighter, 1 year will be longer. And the chemical composition. We know chemical composition from the surface spectroscopy process. And we also have to know physics. We customarily classify this into two categories. One is called microphysics. This is about the equation of state, EOS, nuclear generation rate, and opacity. How opaque or how transparent the material is to electromagnetic wave at certain density and the temperature and so on. These are called microphysics because if we take just a small part of the sun away from it and say put it in our laboratory on Earth, then we can still measure these properties of this material. On the other hand, there's the so-called macrophysics, the convective transport of heat, chemical diffusion. These processes are actually also difficult to simulate too. And in any case, these structures, these physics are determined by the structure of the sun. So we cannot take away a small part of the sun, put it in the laboratory on Earth, and measure these quantities. So these are macrophysics. And actually, there are two rather uncertain quantities. I said we can measure the chemical composition by a surface. Sorry, is there something funny? Okay. A surface spectroscopy. And in astronomy, we often measure abundances of, we say hydrogen abundance, helium abundance, and the rest, which sometimes we call metal abundance, X, Y, and Z. And if you add them all, of course, they add up to 1. And Z over X can be fairly easily measured, but Y is hard to measure. So sometimes we keep it as a free parameter. And then there's the convective transport of heat. Given the temperature gradient, so how much heat is transported to the outside of the sun, and that's not easy to calculate. And the one treatment is called mixing length theory. This is assuming that if a fluid element is hotter than the surrounding and it goes up, it travels a distance, a certain distance, and then exchange the heat with the outside. And by assuming this, we can calculate how much heat is transported. And this length we gather would be we guess would be proportional to the pressure scale height, but not the pressure scale height itself. Maybe so. Let's say it's alpha times pressure scale height. So alpha is another parameter. It will be around 1, but we don't know how big it is. So we have two free parameters, but there are two quantities we have to explain, which is the current radius and luminosity. Okay, do you remember that when we started, we decided we know how much of what was there in the beginning, but we don't know the radius and the luminosity at the current age. So actually, we can change y and alpha this way and that way, so that our model has a current radius and luminosity. The correct radius and correct luminosity at the 4.6 billion years after it became a star. So controlling two parameters to explain two parameters can be done. So we can do it. Right, then why helioseismology? We can build a solar model like I have done. Yes?
There seems to be a question in the chat box.
Okay.
So Sai Vignesh and Gaurav are asking, what makes Y hard to measure in the previous slide, the helium Y?
Oh, the absorption line is weak. Absorption line is weak.
Okay.
Yeah. It's a bit ironical because helium is called helium because it's found in the sun because of this weak line. But still, it's not as strong as say hydrogen lines or certain a metal line. So it makes it difficult to measure. Okay, so yeah, the one problem is when I'm sharing a screen like that, I don't still see the question in chat. Okay. Yeah, it is an observation. It's a spectroscopy issue. So when I'm looking at my PowerPoint slide, I cannot see chat. So may I ask you, Vedant, to warn me if there's a question in the chat box?
Yeah, I'll do that.
Yeah. Okay. Okay. So I'm on this slide. So suppose we build a solar model, and how can we check that if it is correct? We can check that by measuring quantities that were not used to build the model. For example, we can't say the model is correct because its radius is correct. We have just made sure that it is correct. So what are the quantities we did not use to build the model? One example is a solar neutrino flux. Solar neutrino is produced with a hydrogen fusion reaction happening at the center of the sun. And then the neutrino will eventually, some of them will eventually arrive Earth. So some are measured these flux. But the measured flux used to be at odd with a predicted value. Okay, so that some of us thought this is the evidence that the solar model was actually wrong. Okay. Today, we think it's been explained by neutron oscillations. So this is not an issue anymore. But then there's the solar oscillation frequencies. Now I'm coming to that in the next part of this talk. Also, again, when we measure the solar oscillation frequencies and compare them with the predicted value, there are discrepancies. One difference between the neutrino flux and the oscillation frequencies is for the oscillation frequencies, when there are discrepancies, we can use this information to correct the model. And that's what Helio seismology is about.
So there's another question.
Mm-hmm.
How is neutrino flux measured?
Oh, it's going to be a bit long. You just, for example, in the case of the experiment called Kamiokande, so you prepare a huge tank filled with a huge amount of water. Then neutrino do only the weak interaction, so the interaction is not big, but a high energy neutrino can hit electron and cause so-called Cherenkov light, and this can be catched by a photomultiplier tubes, and this way we can count the number of high energy neutrino event. That's how we measure. In Kamiokande, the first one was based on a different principle. There are more than one principle. Okay, so now we're starting on the Helio seismology. So it all happened in early 60s. The Layton et al. This Layton is the author of the famous textbook by Feynman. It's Feynman, Layton, and Son. It's that Layton. And Layton and his collaborators look at the solar surface velocity. Solar surface velocity field, sorry. It's a solar surface velocity as function of position and time. They used a Doppler measurement, and they found an oscillating component. And so the sun is a variable star, and the period is about 5 minutes. It's a multi-frequency thing. And here's a movie from SOHO MDI. It's one of the spacecraft. And now the one on the left is running. Probably you don't see it very well, but now one on the right is running, and probably you see it better. So this is as if the one on the right is as if you just take the center part of the one on the left. And some of you might have seen a movie of Granule. And this, to some degree, resembles that of Granule, but it's different, right? And for the Granule, time scale is 10 minutes. But for this one, time scale is about 5 minutes. And this is a so-called Doppler graph. It's a map of Doppler velocity. And this is the raw Doppler graph obtained by Soho MDI. And if you see the scale, it's covered the range from -2 km per sec to +2 km per sec. And this is dominated by the solar differential rotation. If you look on the left side, the sun is coming towards you. And if you look on the right side, the sun is moving away from you because of the rotation. But there are some patterns. And we want to look at these patterns. So what we do is subtracting a 40 minutes average, 40 minutes running average from this one. And then we end up with this one. By taking a 45-minute average, we can filter out rotation and the slow convective feature called supergranulation, which has a time scale of about a day. For supergranulation, 40 minutes is just an instant. So we have a snapshot of the supergranulation. So we can subtract it. And this is what we get. Now, what shall we do with this signal? This is a funny movie showing the spherical harmonics. As some of you may know, any scalar function on sphere can be expanded in spherical harmonics. Scalar harmonics has two indices. One is L and one is M. And this is for L equals 0, M can only be 0. For M equal 1, L equal 1, M can be either 0 or plus minus 1. And the difference between plus 1 and minus 1 is plus minus 1. Plus 1 is actually when the pattern is rotating clockwise, and the minus 1 is when it's rotating anti-clockwise, and so on for the L2, M, and so on. Okay, here's the same thing. It's showing more patterns. The L equal 20M20, L20M17, L20M0, and so on. Now, so L is a number of nodal lines, and M is a number of azimuthal nodal lines. Okay, if you look at this, the azimuthal nodal line running from North Pole to South Pole is actually there are 20 of them. So there are 20 nodal lines, and all of them are azimuthal. Okay, but what is azimuthal? We don't know what is azimuthal. We don't know where's North Pole and South Pole if everything is spherically symmetric. And these oscillations are nearly spherically symmetric. So if we expand the scalar f on the surface of theta and phi into expanding this into by spherical harmonics, this is the expression of the spherical harmonics, and this FLM will be independent of M for the spherically harmonic, the symmetric case. And from here, for simplicity, we assume we observe the radial velocity rather than the line of sight velocity. The latter is what actually we measure, but just for the simplicity, suppose we measure radial velocity. In the spatial domain, the velocity field can be expanded in a spherical harmonics. V, theta, phi, and t now is just like that what we saw in the previous slide, expanded in spherical harmonics. This time the coefficient will be time dependent, ALM of t. And in the time domain, the Fourier decomposition comes in handy, so let's do it like this. Then we have a Fourier spherical harmonic decomposition. That's what this FSH decomposition, which I didn't explain, means. Of the velocity field, the V theta phi t is now, okay, this sum, and ALM of omega times the spherical harmonics times e to the I omega t. And reverse this transformation, and we can obtain expression for ALM of omega like this. And how does AL omega looks like? Okay, this is what so-called K omega diagram. This is the power spectrum of the solar oscillation. What is plotted is a PL omega, which is AL omega squared and averaged over M. Because M is running from minus L to plus L. There are 2L plus and 1 value of different M's. So hence it's a 2L plus 1. And this is L, and this is a frequency. Actually, it's not omega, omega divided by 2 pi. And the L actually has something to do with a wave number, special wave number. So that hence this name K. It says frequency, but it's related to omega. So this is called K omega diagram. And where it's red, the power is big. Where it's blue, the power is small. And it's bright red in something like 3 millihertz. And this corresponds to 5 minutes. So this is about a 5-minute oscillation. Layton et al. Did not see these ridges, but now we see these ridge structures. Okay? And the full explanation will be too lengthy. I mean, it takes 1 hour of a lecture, but this is a signature of acoustic eigen oscillations, or it is called the P-mode oscillations. You know about eigen oscillations. We have an eigen oscillation mode when waves. Yes. What does the power spectrum actually denote? Okay.
This seems to be a question. What does the power spectrum?
Yeah, okay. Let's go back. So power spectrum is about, sorry, yeah, I actually, I didn't mention it, did I? So there's many components of the oscillations. Say one component is oscillating at certain spatial pattern at certain frequency. For example, if you look at, say, L50, then we're starting from here, and here there's a place where the power is big, okay? And go up, slightly up, another point, and so on. So this tells you where the oscillation is strong. The Weber amplitude is large. So this is like amplitude square of the oscillation mode. Okay. And someone else is asking, but since in general stars are characterized by a convective process, shouldn't all stars be variable? Okay, that's a modern view. Well, except not all the stars have convective envelope. Some stars has only convective core. The envelope is not convective sometimes. Okay. So the convection does not necessarily mean oscillations, but give the modern, the precision of the modern observation of the sun and stars surface motion, then we can say most of the stars are variable. That's true. Okay. Okay, now let's continue. Oh yeah, the eigen oscillation is when the waves that travel inside the medium interfere with itself constructively, right? And this happens only when a certain condition is met, and this frequency is called eigen frequency. You all know about the eigen oscillation pattern of a string. I mean, I don't have to explain it, right? Yeah, you know what I'm trying to depict. So this is the eigen oscillation pattern of a string. Likewise, the eigen oscillation pattern of a sphere would be like that. So here's a sphere, and here's a cut from the front, and a cut also from the right-hand side, and a quarter of this sphere is removed. So this is the surface pattern we are looking at. Actually, do you see my castle? Sorry, I forgot to ask. Yeah, okay. So this is the. Sorry, you are at a network program again. Could you repeat? Can someone else tell me if you see the castle properly?
Yes, sir. Cursor is visible.
Okay. Yeah, okay. Actually, I see more. Ooh, okay. Carbon oxygen okay. Yeah. Neutralization. Yeah, okay. Maybe later. Yeah. Okay, let's limit the question. No. Okay, you can still ask question. If I can catch them timely, I will answer. Yeah. Also, I was saying, so this is the surface pattern, and this is the pattern inside the sun or stars. And I already talked about L and M, which is the nodal line of spherical harmonics on the surface. And here N is a number of nodal surfaces, so the radial surface, like that. Here's 1, 2, 3, 4, and so on. And this N now appears as a index of F. Okay, so the sun is oscillating. The solar Eigen oscillation frequencies reflect interior structure of the sun. And more specifically, the adiabatic sound speed determines the pressure force. It determines when your fluid element is compressed, how strong it will try to come back. This is controlled by actually bulk modulus. This is the adiabatic sound speed time density, but never mind. And if you pick out density alone, the structure of the density profile determines the buoyancy force. And by this means, if we know the solar structure, in particular, if we only know the density profile and the sound speed profile, then we can calculate the eigenfrequencies. And in Helio seismology, we try to reverse the path. By measuring eigenfrequencies, we can deduce the solar structure. And the mathematical tool used in this process is called inversion. Sometimes the entire problem is called inverse problem. Now, let's talk about the Cowling's classification. At high frequencies, the pressure force dominate, and these are called pressure mode or P mode. At lower frequencies, buoyancy force dominate, and these are called gravity modes or G modes. And in between, there are incompressible surface wave modes. Surface wave mode is also buoyancy force, but it's not internal buoyancy mode. And these are like ripples on the surface of a lake. And let's look at this K omega diagram again. So there are ridges, right? And this one is F mode ridge. And this one is P mode ridge with N1. There's one nodal surface hidden in the solar interior. And this is P mode with N2, 3, and so on. And to this date, we don't have any detection of G mode that everyone agrees that it is. Some people claim, but people do not believe them. Now, okay. Sometimes we discuss solar oscillation and stellar oscillations in terms of the ray theory. This is a ray theory of string. You can imagine describing the wave propagation in a string. Well, sometimes it goes left, sometimes it goes right, and so on. At the high frequency, asymptotic limit, the propagation of sound waves in the sun can be well represented by a ray like this. A ray path in the sun is not straight because of the variation in sound speed. So sometimes the wave would travel like this, okay? Because it's hotter inside, the sound speed is higher, so the path will take shapes like that. And if it's plunged into the center of the sun at a larger angle, it can go like this, or even go like that. This is sometimes useful, but we also need a more mathematical treatment. And those of you who are not familiar with fluid mechanics do not have to understand this. But let me tell you, just so we can write down the equation, differential equation. Here, the Gaussian is a so-called displacement vector. During on the course of the pulsation or oscillation, a fluid element which was here at equilibrium will move somewhere else. And this movement is signified by the displacement vector. And we are interested in only the component of the moon motion, which is proportional to the e to the I omega t. And when this is taken out, the rest follows this kind of differential equation. If you look at this part, divergence of the displacement vector is actually determining the compression, actually divergence, how the fluid element is compressed or the otherwise at a certain point. And the rho c squared is called bulk modulus. And you multiply this to this, and you know how much actually a force this is producing, the fluid element. And the force works to a certain point is how strongly the guy next to you is expanding or contracting. So we have to take the gradient. Just like this, actually we can explain all these terms, although I don't do it now. Now, here is a ray pass again. Now let's talk about the rotation of the sun. The rotation of the sun affects the wave propagation. Suppose we look at the sun from the north, it's rotating anticlockwise. And the wave which is traveling on this way and the wave traveling on this way will be affected differently. Actually, this means a positive M and a negative M. This is primarily by advection, but also by Coriolis force, although the effect is small. The rotational splitting, and as a result, the solar eigenfrequencies are shifted. This is the slice of k omega diagram, AL omega squared. And forget these two. These two are leakage. Okay? And here's the frequency, and this is the power for L20 in minus 20, minus 90, up to minus 20. And you see this. Okay. If the sun were not rotating, actually they should all line up like this on the straight line. But actually it's shifted like this. If the sun were rotating faster, it will tilt more. The gradient of this red line is proportional to the rotational frequency. So by measuring the rotational split frequencies, we can infer the internal rotation of the sun. Seismic inference. We can just listen to a musical element and tell what it is. Usually you can tell if it is a piano or viola, right? Because we heard it before. But nobody has listened to an object like the sun. So we need physics and math to decode the sun's tone, timbre. So this is a bit of a repetition of what I said before. The forward problem is when we calculate the sun's tone from its structure or rotation. Inverse problem is when infer the sun's structure from its tone. And here's some result. The sun speed distribution in the sun. Now, this is actually according to the standard solar model. Here it has a radius, this is center, this is the surface. And this is the sun speed squared. And the sun speed squared is proportional to the temperature divided by, so mu is mean molecular weight. And because the temperature is higher and higher, gets higher and higher, if when you travel to the center of the sun, it goes up. But eventually, because the mean molecular weight is bigger at the center of the sun, because the hydrogen is turning to helium, it will begin to decrease. And here is the base of the convection zone, where the temperature gradient changed rather abruptly. Now, so this is the theory. So, and here is what we measure, except it's not displayed in this way. It's displayed in delta c squared over c squared. Delta c squared is a difference in the adiabatic sun speed squared in the sun and the model. So if this is 0, it means sun speed in the sun and the sun speed in the model are the same. Okay. And you see a series of these things. And this vertical bar shows error, estimate error. And the horizontal bar shows the resolution we've got. And this is what we have got. This is for the very modern model. So for this modern model actually agrees with the observation within 0.5% of accuracy, because if you look at this point 0.004, 0.0 minus 0.004. But it's rather uncertain here and here. Look at this resolution. For the reason it's beyond the scope of this talk, because it is about the inversion. It's difficult to make the inference deep into sun. And probably that is something you can imagine. But it's also difficult to measure things very close to the surface, ironically. And what's this pump? I'll come to that later. And here's the result of a rotation inversion. The solar rotation, differential rotation. This is calculation by Gratzmeier in 1985. So he calculated it, and he guessed the rotation of the sun will look like that. And this is what we got. This is two different estimates done by two different people of the same data. Actually, the one on the left was done by me. One on the right was done by late Mike Thompson, who was a great good friend of mine. And the important things is that if you look at these contours, they are the sharp turns in these contours. Okay, so there's surface shear layer, and here there's no columnar oscillation like this, right? And here is also another sharp gradient in the rotation speed. This is called Takoc line. And the inside, okay, so this is the convection zone. And within that, it looks like that the sun is rotating rigidly. So actually, this rejects the previous dynamo calculations. And let's talk about this and that, okay? So here is Takoc line. The the rotation speed is changing rather abruptly. And this usually caused mixing, okay? And the mixing of the fluid. And this shear-induced mixing if is probably counteracting the gravitational settling of helium. And what is a gravitational settling? The inside the sun and stars, heavier elements sink and migrate towards the deeper layers. And you might think this is because of the gravity, but it's not. In reality, what happens is a lighter element diffuse upwards faster than a heavier element. You know the diffusion. If you have more of one thing here and less of the things like otherwise, then it will spread. Think of a cigarette smoke, although I don't smoke anymore. Smoke spread due to diffusion. If you look at the sun, because the density is higher in the center, there are more hydrogen in the center, more helium in the center. The hydrogen wants to goes up, helium wants to go up too. But this is determined by the thermal velocity of these molecules. Sorry, in case of the hydrogen and helium, it's just proton and the alpha particle. And the alpha particle will be slower because it's bigger. Okay. So the hydrogen is going upward faster than helium. So it is as though helium is being left behind. And the overall effect, when you take account of the fact that the overall has in hydrostatic, then the net result is that the helium sinks. And the modern standard models take account of the helium accumulation beneath the base of the convection zone. So the mean molecular weight is increased there, and the sound speed is decreased there. But if, because of the mixture caused by, mixture caused by this shear is putting some helium back, then the mean molecular weight here is not as big as it is in the standard model. It is smaller. Then the squared sound speed, because it's roughly proportional to the temperature divided by mean molecular weight, will be bigger in the sun. And we think this is what we are looking at. Okay, now on a different topic. Local helioseismology. So let's forget these global modes like P mode and so on. We can try and direct measure the surface propagation of wave. There are two pictures. Let's take this one first. This is a bit like a ray theory. So a sound speed began to repeat here, and then ends up here. Begin here, then if it's with a different angle, it will end up here with after time t, or time after time t3. And we can actually measure this travel time by taking a correlation of oscillation at these 2 points. And if beneath the surface there's a flow like that, waves going rightward and waves going leftward will have a different path. So they will show a different travel time. And let's forget about this new opportunity for the moment. I'm not explaining about that. And by this, we can measure so-called meridional flow. Meridional flow is like that. It's perpendicular to rotation. It's perpendicular to rotation. And we believe that it's important for understanding a solar dynamo. And at the surface, it's poleward, and it's up to 20 meters per second. The rotation speed was about 2 kilometers per second. Remember? So this is 1% of it. And this is the one measured by Peter Giles in 1997. And now we can measure meridional flow even inside. And this is the one result obtained in 2013 by Zhao. Okay, here the red part is going this way, and the blue part is going this way, and the red part is going this way again. So meridional flow is not like this, where there's only one cell. Probably there are two cells. So this is in 2013. But in 2021, Guizon said, no, it's single cell. They are basically based on the similar data, and the analyze method is similar but slightly different. And then recently we did another work. What is shown is a hot and external simulation of the solar rotational frequencies. And here it is shown, only the rotational frequency is shown, but we have the 3D velocity field inside sun simulated by hot and external. And we carried out inversion with a constraint based on hot and external. In a nutshell, we demanded that it should not be very different from hot and external. Then actually we get a double cell result. So this is still an open issue. And here's another open issue: convective speed. Hanasoke Divan and Srinivasan in 2012 tried to measure convective velocity based on a local Helio seismology. So what they did is, okay, here's the two surface points, and they measure travel time. They measure the fluctuation of travel time because they saw that it would fluctuate because of the convective motions, okay? But actually they failed to measure it. So this is okay. So actually that should give the upper limit of the convective speed. We can say that if we didn't detect the convective speed, then convective speed should not be as fast as this. So they measure the upper limit of the convective speed, which is plotted here on the lower part. This red part and the blue part and red part correspond to a different depths. And this is the upper limit. And this is one of the modern computer simulation. And they differ by factor 100 here. If you go to the right, which is actually go to the smaller and smaller scale, actually this is L is the same as the spherical harmonic cell. Actually the discrepancy becomes smaller. But this is a big discrepancy. And we don't know what is causing this still. Okay, and I think I'm running late, but let's move on to asteroseismology. Okay, it's asteroseismology, not asteroseismology. Be of that. And in principle, the very basic principle of asteroseismology is the same as the helioseismology, but there are some differences. In helioseismology, we can do spatially resolved observation But in asteroseismology, it's probably impossible for foreseeable future. And the number of modes in helioseismology, we deal something like 4,000. In asteroseismology, certainly less than 100. And limited to only L, I mean the spherical harmonic degree of 0, 1, 2, maybe 3. The mode, as I explained, we observe only P mode, acoustic mode, and the surface gravity wave mode. But in stars, because there are many stars, in some stars we measure G modes too. And excitation, I didn't mention this, but the solar oscillation is excited by turbulent convection. The convective motion emit sound waves, and that is the cause of the 5-minute oscillation. In stars, well, there are just many different mechanisms. And do we measure these things just for probing interiors? In the case of the sun, yes. But in asteroseismology, it's not always so, because there are many interesting stars, and even how they pulsate can be a matter of scientific interest. And there are many stars, but let me just pick just one star, which is called KIC 1114512 And the name means the number 1114512 in the Kepler input catalog. And Kepler was launched in 2019, and it has found a lot of exoplanets, you know that. But it has also been used for asteroseismology. And this particular star is here in the constellation of Cygnus. And its Kepler magnitude is 13, and according to Huber et al., the effective temperature is 8,000. The surface gravity is like log G is 4, and it is a late A star. And here is the oscillation amplitude spectrum. This is from the observation more than 1,000 days long at a 30 minutes cadence. And in this star, we observe G modes and we observe P modes. This is a blow up of these two ranges. And we try to build a model that explains these observed frequencies as well as possible. And the model we found has the following properties. It's slightly massive than the sun. It's twice as big as the sun. And it has a convective core in the internal 5% of the star. And when we look at this initial abundance, you remember this, how much of what? Z, the metal abundance is 0.01. The helium abundance is 0.36. Now this is too high. You don't see that high concentration of helium in just around the corner. So this is strange. Such star cannot be born in the modern environment. So we wonder if this is a blue straggler star. And the blue straggler star was found in a globular cluster. This is the HL diagram for M3. And here's a turning point. Because of the position of the turn-off point, we know this globular cluster is about 8 billion years old. So this is the main star. This is, red giant branch, an asymptotic giant branch, and the horizontal branch. But here are some stars left. So what are they? So some thought these are young massive stars yet to depart the main sequence. But this means a later star formation event profiling a very narrow mass range. And there's no supporting evidence for such a process. So probably it's not the case. Another possibility is probably these are stars that are undergoing or have finished a merger event. Hence the higher masses, or maybe just mass transfer event from a companion stars. But in any case, so these stars migrated from another place in the HL diagram. So we wonder if this is a blue straggler star. Blue straggler star, what maybe, but this star is not associated with a cluster. So that's a problem. Because if a star in a cluster, then it will have stars around it to merge or have a mass transfer from. But this star is standing alone. Anyway, let's go on. These are rotational splitting. And actually, here I'm saying actually these are triplet. Actually, there's a you see something here. So it's 1, 2, and 3. M-1, 0, +1. And using this, we measure the rotation of this star. The rotation period is about 100 days, and there has been a series of work. The rotation is nearly rigid, but the outside is rotating slightly faster. That Coates et al. 2014. And later, actually, we think the core is rotating much faster. Hutt et al. 2019. And Hutt et al. Revisited this issue later with a different approach and confirmed this result. So this is picture, kind of picture of the rotation of this star. In the unit of omega 100, this is a rotation rate for a 100-day period rotation. In the bulk of the star, it is like the 93% of this rate. Here, it's slightly faster. And in the center, it's 6 times faster than this. And this nearly rigid rotation suggests a strong angular momentum transport. And the one possible mechanism is a magnetic field, but the star is unlikely strongly magnetic because it has only core, convective core. And also, if it's so strong, the modulation in the light curve would be observed. And if the envelope is really rotating faster, why? Maybe it's an angular transport by waves, which may be exotic to some of you. There's a viscosity type mechanism, but it cannot spin the outside up the up over the internal rate. It's easy to imagine that in the beginning, the center is rotating faster than the outside. And then due to a certain kind of viscosity, the outside can goes up and the center can goes down. But it never, outside can never overtake the internal rate, right? So it's something different. And the one thing is this mass accretion idea, the blue stragglers idea comes. Maybe if this is due to some angular momentum taken in from outside, then probably it can explain. Okay, but this is still an open issue. And then let me talk about sphericity. You know, the sun and most stars are nearly spherical, but not always perfectly so. And the seismic data can tell us about the sphericity of the sun and stars, because the frequency shift will differ from mode to mode. Okay, here I plot 2 mode, L2M equals 0 mode and L2M2 mode. And these are different patterns. And suppose there's some strange feature on this surface of this star. Then this mode and this mode certainly react differently to the presence of this, say, hotspot, right? So I already told you about the rotational splitting. Suppose this represents again frequency. If there's no rotation, there's no asphericity. For L equal to, the frequency will be the same for all the value of M. If there's a rotation, it will split like this, okay? And if there's a sphericity, actually there are more shift to these levels. The thing is, for rotation, there's these has auto parity. The shift for M1 is the same as shift to M-1. But the asphericity does not know the sign of M. So the M1 mode and M-1 mode are affected in the same way. Okay, Halo seismometry has nothing to do with the coronal temperature. Sorry. Yeah. So we can measure asphericity, and we did it. And the star is measurably oblate. The equatorial radius, difference between equatorial radius and polar radius, divided by its average radius, is at the 1.8 plus minus 0.6 times 10 to the minus 6. So it's barely a 3 sigma level, but it is a detection. However, from the rotation alone, it should be more oblate. It should be bigger. So this is too small. So something is rendering the star less oblate, at least to the waves. Okay. And the magnetic field certainly can reduce the oblateness. If the magnetic field exists in the polar region, the equatorial region, it can reduce it. And it doesn't have to be strong at all. But unlike the sun, this star only has a only very thin convective layer across the surface, and most of the convective layer is in the center. So could it be a fossil field? Maybe. Maybe it's a fossil field. And this time, the blue straggler hypothesis is not helping. And another thing, and the reliability of the model still worries us. And if the star has really undergone a merger event, modeling based on a single star evolution is not adequate. But the direct simulation of such a process is very difficult. So we tried a procedure to perturb a stellar model chemical composition. This is what I did my student Hatta. You have seen this name often, 2021. And by exploiting a set of mass used for stellar pulsation theory, interestingly, and we came up with a model. And the result is kind of gray. The model explains observed frequencies well, but not much better than a standard model. So we cannot say this is better than a standard model, but also we cannot say this is a trash. Okay, so it's a moderate amount of success. So in summary, we can probe the interior of the sun and the stars using waves. And in helioseismology, we already know a lot about the very basic of the internal structure of the sun. The solar neutrino problem has been probably solved. The standard model is basically okay, but we are still very ignorant about the dynamical process working in the sun, such as the meridional flow. And the KIC 1114523 was an example of asteroseismology. It's a nearly rigid rotation, but the surface rotates a bit faster, which is a mystery. And the core of the star is rotating fast. This is not quite a mystery. This is to some degree natural. The star is oblate, but less so than its rotation implies. Magnetic field in a star without an extensive convective envelope? Well, we don't know. And also, we might have found a solitary blue straggler, and this is a mystery. Okay, so that's the main part of my talk. Maybe I should take scientific questions now. Okay, Vedant is cut off again. So maybe you can just ask.
Okay. So does anyone have any more questions? I don't think so.
Yeah. Okay, maybe I answer one of the former question about neutron oscillations. Okay, neutron in standard particle physics theory, the neutron is massless. Okay. But some things actually neutron may have a mass. And when they have a mass, they flavor, they're so-called flavor oscillations. Actually, I just mentioned neutrino, but actually there are three types of neutrino: electron type, mu type, and tau type. If neutrinos are massless, then what is born as an electron type neutrino is always be electron type. Mu type will always be mu type, tau type, tau type. But when there's a mass, they oscillate between these three states. So what was born as an electron neutrino at the center of the sun may change to mu neutrino, tau neutrino, back to electron neutrino, and mu neutrino again by the time we detect it. So this is a neutrino oscillation, and it's how it can explain the deficit of apparent neutrino flux. Okay, then, sorry, my time is actually up, but let me talk briefly about the admission process at Sokendai. Is it okay, Vedant?
So there's one more question now.
Okay. How has it been conducted on a larger sample of stars? What result do we see from them? Oh, yes, of course. So we with Kepler catalog, with Kepler data, we are studying a lot of stars. And because all these stars are all different, we can't say the result was like that. It's very different. But actually, the one thing I can mention is one result we're getting is that the differential rotation in stars are not as big as we thought. Okay. And the result we got from the KIC 1114523 is an example which is going against this trend. So that's one thing we are learning. And I think that's all we can say. I think if we want to know what we learn about these stars, I have to go through one star by another star. Sorry about that. Okay. Thank you. Okay, then let me change the yeah. Where is it? Okay, I tried to be as brief as possible, but when I started this.
No, the talk itself started 10 minutes late. So.
Yeah, okay. Okay, so do you see it? It's saying admission guidance. Okay.
Yes, sir.
All right. So let me start. This presentation is a very quick guide to the admission process at the Astronomical Science Program, Sokendai. And the more detail can be found at this page. Probably, if you already not aware of this URL, I can probably send you later. Let me talk about our program. NAOJ, National Astronomical Observatory of Japan, is arguably the National Center of Astronomy and Astrophysics Research, with more than 150 researchers, a large-scale observational facilities such as Subaru and ALMA, and involvement in space missions and supercomputing facilities. And NAOJ doubles as Astronomical Science Program Sokendai. Sokendai's headquarters is in a different place, so we are NAOJ and Sokendai at the same time. And there are 119 researchers associated with the program, and they are NAOJ researchers, top in their fields, and Sokendai teachers at the same time. And we are also covering a wide range of topics. And in our program, there are currently 36 students, and 5 of them are from abroad. 1 from Brazil, 1 from India, 2 from Indonesia, and 1 from South Korea. Oops. And in our program, there are 5-year course and 3-year course for PhD. The 5-year course is for someone finishing undergraduate study or someone already finished. The 3-year course is for someone about to obtain a master's degree or someone who already have one. To study here, first you need to find a teacher you wish to work with. So if you go to the website I already introduced you and go to this page, there's a list of supervisors explaining what their research topic is. Find one you want to work with. And you also have to pass the entrance exam. Also, you need to find a way to support yourself financially. And this is an issue separate and yet coupled with the admission process. And the story gets very complicated from now. Sorry about that. Now, financial aspect first. There are 2 cases. One is the MEX scholarship. MEX is the Ministry of Education, Culture, blah, blah. Namely the Japanese government scholarship. And the MEX use the word privately funded. And this actually means all the non-MEX source of money, which they call private. It could be a scholarship by your own government or some private company. Or of course, it can be your family support. Or the lottery money you won. It doesn't matter. And okay, so how does the MEX scholarship? Okay, sorry, once again, there are 2 cases. One is university recommendation, and the other is embassy recommendation. Either way, if you got a MEC scholarship, you'll be paid this amount per month, and your admission fee and tuition fee will be paid by Sokendai. With this amount of money, you want to live like a millionaire, but you can survive. Now, let me first talk about the university recommendation. First, you take our exam for overseas student. This is exam we do in December. Now, if you pass, we will recommend our recommendation to MEXT. Actually, I recommend you to Sokendai headquarters, and Sokendai headquarters will recommend you to MEXT. And MEXT may or may not award you a scholarship. It's not under control. But if you are awarded a scholarship, you are in. October admission only, not in April. So you take the exam in December. We will tell you almost immediately if you pass our exam or not. MEXT will have their result in May, actually, and then you come to Japan in October. And this is available only once in a while to our program because Sokendai only has a few slots. Now, the embassy recommendation. The first, you go through a screening process by your local Japanese embassy. If you pass, you will come to Japan as a research student, not a regular student. You're very careful about it. And you can come either in April or October, it doesn't matter. But now you're living in Japan. Then you take our standard entrance exam in August, or sometime in January if you are going for the PhD course, sorry, the 3-year course. April admission for the 5-year course, August exam. April or October admission for the 3-year course, either August or January. Okay. And let me talk about the entrance exam. As we have seen, there are 2 kinds of exam. If you live abroad, you take the exam for overseas student. If you apply for the MEXT scholarship by university recommendation, if you take this to be recommended by us to MEXT. And if you are privately funded, you take this to be admitted, actually. Because we don't have to ask MEXT to award you anything. You pass our exam, you are a student. But if you need a MEXT scholarship, well, you have to wait until if MEXT will give you a scholarship or not. Now, if you live in Japan, you take the standard exam just like a Japanese applicant. And if you're with a MEXT scholarship by embassy recommendation, you have to take this exam to be a real student. If you are a research student, you are just a research student. You will not get a degree. You have to be a real student. For that, you have to go through this. And the exam for 5-year overseas student. So this is the one we do in December. For the 5-year course, you submit your English score and the GRE physics score. And then there will be an interview. And here's an asterisk down here. Not if you are English speaking and privately funded. By English speaking, actually we mean educated English in higher education. So most of you are English speaking in our mind. And actually, we know it will be reasonable to waive you from these English scores, but the MEXT stupidly insist on these scores. So if you want a MEXT scholarship, you still have to submit this. And for the 3-year course, the same thing for the English score. And then there will be your master thesis presentation, which is followed by an oral exam and an interview. Okay. And the oral exam, sorry. And the more detail of the exam. This is a standard exam, sorry. So you take this if you're a research student here. For the 5-year course, a written exam for English, and a written exam for math and physics, followed by an interview. And in this case, I'm sorry, we can't waive this exam for you because we actually add these scores. Yeah. Last summer, it was embarrassing. We had to ask a native Irish student to take this exam. Yeah. he kind of did it. And this is followed by an interview. For 3-year course, a written exam for English, and your master's thesis presentation, and an oral exam and interview. Sorry, I should have put this in the previous slide. The topic of oral will be a general physics, astronomy, and math. Typically, you will be shown a few pages of English document discussing something. And later, I will discuss about the content of that document. So, if you wish to study here, you need to act fast because overseas admission is a long and slow process and complicated, as we have seen. So if you decide to apply today, the earliest possible admission will be April 2025 for privately funded student. October 2025 for student with a MEX scholarship due to university recommendation. For both, the entrance exam will be December this year. And the earliest possible will be October 2025 if you are for 3-year course, or April 2026 admission if you are aiming for a 5-year course for the MEX scholarship and the the embassy recommendation. And this is preceded by a period as a research student starting in April 2025. And remember this, details varies with how the Japanese embassy in your country handles things. It varies. So the Japanese embassies in India may behave pretty different from the Japanese embassy in Korea. So you have to contact them quick. So the first thing you need to do are find a teacher. Okay. And if you're going through the MEX university recommendation scholarship, ensure you have these relevant scores in time. Look up the exam date in your area. And if you're going for the MEX embassy recommendation, contact your local Japanese embassy as soon as possible. Okay, that's it.
So I think for ISRB students, the 5-year course is not relevant since we have a master's thesis in the 5th year.
Mm-hmm. Yeah.
So I think for us, only the 3-year course is relevant, right?
Okay, but here's the advice. I hope. Okay, I mean this in very good intention. Okay, in the past, we have had some applicants from India with these master degrees. Let me be frank with you. The level of this master thesis varies a lot. And if you are going for a 3-year course, and if you cannot produce a good master thesis, actually you'll fail. So if this is the case, actually it may be better to go for a 5-year course. So if you are seriously considering coming to join us at Sokendai, you find a teacher first, and then consult us. And of course, this may not appeal to you. Whatever, I want to go to a 3-year course. That's understandable too. But be careful, please. Yeah.
So does anyone else have any questions?
Sorry, I didn't say too much about the privately funded case. If you're privately funded, you still take the December exam, and then you start. You can start in April. You can start in April, yeah. Or if you prefer, you can delay your starting date until October. Okay.
Yeah, so I don't think there's any more questions. So thank you so much, sir, for
thank you for your attention. Yeah.
We are honored that you agreed for this. Thank you so much.
No, it was my honor, as I said. Okay, thank you.
Thank you.
Bye-bye.
Bye.